LangGraph's interrupt mechanism enables dynamic execution control by pausing graph processing at specified nodes and awaiting external input before continuation. This pattern facilitates human-in-the-loop workflows where conditional approval or data validation is required during runtime. The upcoming code demonstrates how to configure runtime interrupts by specifying nodes where execution should pause before or after processing, using a thread identifier for state persistence. You'll see how the graph initializes with interrupt points defined, executes until reaching a breakpoint, and then resumes with the same configuration to maintain state continuity.
Config equals configurable, threaded, some thread, hash run the graph until the breakpoint, graph invoke, inputs, interrupt before equals node A, interrupt after equals node B, node C, config equals config, hash resume the graph, graph invoke none, config equals config.
This code demonstrates runtime interrupt configuration in LangGraph, allowing flexible control over graph execution flow. The pattern uses interrupt before and interrupt after parameters during graph invocation to create dynamic breakpoints, pausing execution at specific nodes. This approach differs from static breakpoints set at compile time, offering more flexibility for debugging or human-in-the-loop scenarios. The configuration shows a thread-specific execution using threaded in the configurable settings, which maintains state persistence across invocations. When the graph hits an interrupt point, it pauses and waits for external input before resuming. The second, invoke call with none input demonstrates how to resume execution after an interrupt, using the same thread configuration to maintain continuity. This pattern is particularly useful for debugging workflows where you need to inspect state at specific points without modifying the graph structure. The trade-off is that runtime interrupts require explicit configuration for each invocation, whereas compile-time breakpoints are set once and persist across all executions. The approach shown here provides fine-grained control, but requires careful management of thread IDs and interrupt points. Let's break it down.
Threaded, some thread,
Assigns a string value, some thread, to a key threaded in what appears to be a dictionary structure. This creates a simple identifier mapping where the thread identifier is explicitly set to this specific string value.
graph invoke,
Invokes the graph's execution with the provided input, triggering the processing pipeline defined in the graph structure. The method initiates the graph's workflow, passing the specified input data through the connected nodes and edges according to the graph's configuration. This is the entry point for executing the graph's logic, where the actual computation or processing begins based on the graph's design.
interrupt before equals node A,
Specifies that execution should be interrupted before processing, node A, preventing the workflow from reaching that node under the current conditions. This parameter controls flow behavior by creating a conditional breakpoint in the graph traversal.
interrupt after equals node B, node C,
Sets the execution to interrupt after either node B or node C completes, allowing early termination of the workflow once one of these nodes finishes processing.
config equals config,
Passes the config variable as a keyword argument to a function or constructor call. The line demonstrates parameter passing where config is explicitly named as the argument, ensuring the receiving function can access the configuration data through this parameter name.
graph invoke none, config equals config,
Invokes the graph with no input data and passes a configuration object to control execution behavior. The none parameter indicates no initial input is provided, while config specifies runtime settings for the graph execution. LangGraph's interrupt mechanism provides dynamic execution control by allowing you to pause graph processing at specific nodes and await external input before continuing. This is achieved through runtime configuration using interrupt before and interrupt after parameters, which create flexible breakpoints that differ from static compile time alternatives. The pattern leverages thread-specific execution via threaded to maintain state persistence across invocations, ensuring continuity when resuming after an interrupt. While this approach offers fine-grained control for debugging or human-in-the-loop workflows, it requires explicit configuration for each invocation and careful management of thread IDs. The key insight is that runtime interrupts enable conditional workflows without modifying the graph structure itself, trading one-time setup convenience for dynamic flexibility during execution.
The graph pauses at node A, skips node B like a stone, then crashes into node C, all while hugging its threaded